So, good morning. Yesterday, there is a small mistake while taking this particular thing. So let me quick go through about the complete binary search algorithm, how to apply that particular binary search algorithm. Let me apply very quickly. Then you'll get some kind of idea regarding to binary search one more time. So how the things are being gets happened here. So let us see. Let us say this particular thing for a while. Then so look at this element to be searched within a given list of elements will be 20, and these are the list of elements which are available with you. Yesterday it has been discussed. It was discussed in today's class. But yesterday we find a small mistake at the end. So I have resolved that particular small mistake. So today we would like to go ahead. So first one is A of 1, and the last one is A of so last equal to A of 13. That is the element. Then here, first mid value must be identified as far as the binary search is being considered. So therefore, mid value will be equal to 7. So therefore, so mid could be gets identified with A of 7 or elements of 7, list of elements of 7 here. It's been seen in the previous class. Now, we'd like to check for the mid element whether it is gets true or false. So f mid equal to required element, that is 20, 70 is equal to 20. It is absolutely not. So therefore, the condition will be considered as false. And then so f element is less than f mid, yes, it is true. So therefore, the problem will be reduced something like this. The problem has been reduced to something like this: 1 plus 6 by 2. So this by this 3. So the problem will be gets reduced here. Gets reduced here. Okay. Up to that extent, the problem will be reduced, and the left-hand side problem will be taken into consideration. 70 is already set with so first search operation by A of mid. So that is not the A of mid is not equal to your required element. So that we'll take left-hand side sublisting. Now, I'd like to take these two. So element is f mid equal to our required element. Now it is not false because 30 equal to 30 equal to 20. It is false. Therefore, we'd like to check one more second condition, that is element is f less than f mid. Yes, it is true. Element is 20 and f mid equal to 30. So therefore, it could be true. So therefore, we'll go ahead and check out this one. Here, first element will be set to A of 1, and the second element will be mid minus 1 will be set to last element here, 1 plus 2. Now here, we'd like to calculate the A of mid value. So that is A of mid equal to 1 right now. Okay, A of mid equal to 1 right now. So it could be seen in such a way, and A of mid equal to 1 in the sense 1 plus 3. So 1 plus 2. Previously it is 2. So 1 plus 2 divided by 2, that is 3 divided by 2 will be gives you 1 here. So therefore, first element will be 1 and the mid also be equal to 1. Okay, it is being identified. So therefore, because of this particular thing, so some more problem will be reduced with some more on elimination of 4 and 5 elements from the specification here. Then if mid equal to element or not, that is 10 equal to 20, it is false. Then element is less than f mid, that is 20 is less than 10, again it is false. Then it is going to check for element is greater than f mid. Yes, it is true. Yes, it is true. Therefore, first will be gets adjusted towards mid plus 1 in the sense of 2, and last is already checked with already, it has been there with so 2 here. Okay, so here then like to identify, so what is the next element to be taken into consideration here. So mid element will be equal to again 2, that is 2 plus 2 divided by 4 by 2, that will be equal to 2. Therefore, mid element will be equal to 2. So now it has been eliminated previously. It has been eliminated previously. Now the list will be reduced to 30. So we have only already 10 comparison is gets over. So this could be available here. Then here first will be, so you have 1, 2, and second also you have 2, mid also you have 2. Now the search element will be whether the f mid equal to element or not. Yes, it is true. Now the problem is get successful, or the search is get successful here. In this way, we'd like to identify the elements are successful search or unsuccessful search also be done by taking one more example. So you can see I have already given in the previous sorry, next to next slides we will see. Okay. This is actually some small mistake was happened in terms of doing some kind of exercise. So in this place, so that is why I have adjusted. Okay, however, we'll go for today's class without any further delay. Already we have seen this particular problem today. Now, I'd like to take some more set of elements, which maybe includes negative numbers, positive numbers, and so on and so forth. Then how the things will be gets happen. Let us have a look here. So let us consider 14 elements are there with me. So let us consider the problem complete space will be 14 elements. And these are the elements. Elements will be minus 15, minus 6, 7, 0, 7, 9, and so on and so forth up to 151. So look at this particular, if you go through this list, this list is already in non-descending order, that is ascending order. It is already in sorted order, that is ascending order. So there is no problem to apply binary search on this particular list of elements. Okay, there is no problem at all. Then, so let us consider, we'd like to take 2 to 3 different cases, how the things will be gets happen when the same list is going to put place here. In part 2, what we are trying to explain here is explanation will be took place to apply decision tree of binary search for 14 elements. So how the decision tree is going to be plotted for 14 elements. I'm talking about n equal to 14, not more than 14, not less than 14. So you may be given some exercise or let me say assignment to you people. So if number of elements will be equal to 32, what is the decision tree? Number of elements will be some 6 or 7. What is the decision tree for those two? You may be write some assignment. I'll give you in the afternoon after completion of this class. However, you can see. So right now I am trying to search for one particular element. That element will be 151, which is last and final element. Okay, that is the last and final element. Let me eliminate this one here. So I'd like to identify whether 151 is available or not. Okay. Now let me eliminate this one also, because so I'd like to take some explanation at this particular point. So let us see. So, however, how the things will be gets happen in the first iterative call. What is being happening? Low will be equal to, this is actually low or first. This will be actually equal to high or last. You can take anything here, high or last. Okay, low will be equal to 1 and the high will be equal to 14. Then the mid element will be 7 here. 14 plus 1, 15 by 2, which is in floor value. 15 by 2 is actually 7.5. So the 0.5 will be eliminated from the value, so that you could get this is mid element. Now I'd like to check for whether 3 conditions are there. I'm writing those 3 conditions. So f mid equal to f. Let me write it as f mid. M in the sense. Please consider that m equal to mid. So f mid will be equal to required element or not. Yes, it is correct or wrong. We'd like to check that. Actually, that is wrong. That is wrong in the sense 54 will be equal to 151. so which is false. Since it is false, what we are trying to perform, that will go ahead. So next condition will be, so element is less than A of mid or not. That is, so element is 151. 151 is less than 54, which is again false. Which is again false. The third condition is element is greater than A of mid or not. So, so this could also be, so this could be considered as 151 is greater than 54. Yes, it is true. So because of true, what we are trying to perform, so mid element will be, so low element will be transferred right away from this particular position to this particular position. So therefore, here it is. Right now, it could be considered as the low, mid plus one. Okay, and then what we are supposed to consider, this list of elements will be eliminated from our search space up to this particular area. So this whole list of elements will be eliminated from our so search space here. Now we will consider that in the second recursive call, we'd like to go ahead. 8 is the low and 14 is as it is. Then it is 11. Now mid element will be low is this one here. Mid element will be 11. So same process will be continued recursively for several number of times. So therefore, you could get the answer. How this could be there in the sense that again low value will be readjusted. Low value will be readjusted at this place, so that this list of elements will be eliminated from our search at this moment. Of course, so this one also eliminated from our list. Then this is right now, this is low, and identified mid will be, this is the mid element in the next place. Then also not considered. So it could be taken in the next recursive call. So it could be taken. So low, high, mid, everything will be taken. Mid also be taken this one. So therefore, finally, the search will be successful. Why I have given this particular point here? What is the basic point I would like to take into consideration of this table here? This table is very, very important for us. This particular table is very, very important for us. Let me take some other color, and I'd like to write something here. Initially, at the first time, while recursive call is being gets happened, so this is the first search which is being gets happened on the list of elements. Okay, and then second, so the second search operation will be done at this place on 11. So you can see 7 will be the first mid and 11 will be the second mid. So this will be the second search operation which is being gets operated. And then since it is not identified, and then it will be goes to 13. This is the third search operation which is going to be happen. So here also same condition, so that list element is not equal to A of mid and which is greater than. So in the fourth search operation, this is fourth one. You can identify. Decision tree will be always taking care about the search of mid elements. The search of mid elements. I'll give you the decision tree at this moment. So you can consider that 7 will be the first and foremost element which is being searched, and it will be taken at the right list. So here it is 2. So here it is 11, not 2. Sorry. This is 11. Next search will be done 11, and followed by it is also not satisfied with your required element. So then it will be goes to search for some 13. So after this, it will be goes for some 14. This is the decision tree, partial decision tree for required element will be, the required element will be 151. First, it is going to search with 7th position. Then it is going to search for 11th position. Then it is going to search for 13th position. And finally, it is going to search for 14th position. Therefore, here the search will be get successful. Element is 5. Okay, element is gets 5. This is the decision tree. Partial decision tree for element will be equal to 115. sorry, 151 in this particular example. Then we'll go for some more. So same example, and now I'd like to search for minus 14, minus 14. Okay, so x equal to required element is minus 14. So somehow this is so low, and this is high, and based on this one, mid element is this one. Okay, you can see here mid element is 7. So A of mid 54 is equal to minus 14. No, it is not. It is not equal. So therefore, greater than or less than. Of course, minus 14 is less than value only. So therefore, the high value will be readjusted at this particular place. That is high, and this whole I'm thinking that yes, everything is there in our mind. Just before we have discussed, and yesterday we have discussed. So that is why algorithm is there in our mind. So that is why I'm directly specifying in this example. So this list of elements will be eliminated from our search space. Now, in the second recursive call, so low value is 1 and the high value is 6. So that next search will be gets happened. Next search operation will be gets happened at this place, this mesh. Then here also the condition is gets false. Then still minus 14 is less than. So then high will be adjusted to this particular area. High will be gets adjusted to this particular area, and therefore this list of elements will be eliminated from our search space in the second recursive call. Okay. Then in third recursive call, so what is being happening in third recursive call? So low equal to this one, high equal to this one. So therefore mid value equal to 1. So here mid value could be taken in this particular area. It's also not true. Then everything will be get set up. Okay. So therefore, if you observe this particular table, so what is the mid element which is being taken in each recursive call? In each recursive call, what is the mid element here in the sense? You can see here also, so it will be taken 7 will be the first and foremost search operation which could be done, and then followed by, so it will be taken 3 will be, it is in the left hand side of that particular list, so therefore it could be taken 3, and then followed by it could be taken so 1, it could be taken in 1, and then it will becomes to this area, that is so 2 here. So therefore, even after checking 1 and 2, you could not identify the value. So therefore, it will be considered as not found. This is the decision tree for the element which is being searched by this list of given list of elements. For example, will be taken minus 14. So minus 40 is not really existed within the list of elements. So that by taking first mid will be 7, second mid will be 3, third mid will be 1, and followed by fourth mid will be 2. So there is the matter because high, low, and mid has been identified the same element. So therefore, it could not be identified. So therefore, the search is unsuccessful or element is not found. Okay, this is one more so example to draw the decision tree. And then we'll go for one more. For the left hand side, we'll go for one more. You can see. So 1 and 14, same 7. Then 1 and 6, so same 3. And 4 and 6, so we'll take 5 here. I hope that you people do understand so what this particular actual problem will be, because this is the third example which we have to set for an element that is 9. So these are the search operations. So therefore, the search, what you call search decision making search tree will be seems like this. First, it is going to check with 7. Then it will be going to check with 3. Then it is going to check with 5. 5 is right side of 3. So therefore, here it is 5. Yes, at 5, element 9 will be gets existed. So here your search is so successful or element is so found. Okay, this is the search spree decision making tree for the element 9. For the element 9. In generic way, so if you consider these are the 14 elements which we have with us, then for any kind of element which is successful or unsuccessful. For example, we have taken minus 14, which is unsuccessful, and 151, which is successful, 9, which is also successful. So whatever the successful or unsuccessful kind of binary search operation, then so in generic way, how the decision making tree for binary search, let us see. Let us say this one. These are the elements, and these are the. So these are the actually indices. These are called as indices, and these are actually data or elements. And this is the search operation. Okay, consideration on search. On okay, let me call it as let me call it as let me take it as let me call it as on mid element. Okay, so here somehow if you consider 1 plus 14, that is 15 divided by 2, only one search operation will be done so at this level. Okay, first search operation, either the element will be at right side or left side, that doesn't matter. First operation, search operation will be done at 7. If element will be towards right, if elements will be towards right in this area, second mid element will be this one here. Okay, second mid element will be this one. Still element is at right side, so third mid element will be this one here. Still element is left side, right side, fourth mid will be. After taking 3, the element will be at left side, next will be. Okay. So after taking 2, hope that you do understand. After second recursive call, element will be left side. Element will be, after taking this one left side, then this is the mid element. And it will be right side, this is the mid element, and again left side, this is the mid element. Hope that you do understand. Hope that you do understand. Let me give you one more time. Let me give you, because it may be somewhat a confusion. Many people could not understand this particular thing. There is a possibility to check for, 151 already seen. If you want to check for what you call 112, this is the element I would like to search. So initially it is going to search with 54, I mean seventh index, and it is not equal, it is not true. So therefore element is greater than 54. So therefore we will take the forward direction, I mean right side direction. In this right side direction, so what is the second search which is being happening with the right sublist right away from 8 to 14. So what is the 8 plus 14, that is 22. 22 divided by 2, that is this one here. This is the second search. This is the second search, second mid operation, while the problem is progressively continued. So here 125 is not equal to 112. So therefore, it will be goes for whether element is less than, yes it is less than. So after taking this one, you will move forward, backward, that is left side of second sublist. Therefore here, so what do you call, this is low element, and now this is high element. 18 by 2 in the sense that is 9, third search is being happening here. Third search is going to be happening here. Now, 112 is equal to 101? No, it is. Then whether element is less than? No, it is. Then the element is greater than? Yes, it is greater than. When greater than, again it will be goes to the right side. So right side in the sense, before going to right side, so low value will be adjusted here. This is low value, and obviously, so mid value also be same. Yes, A of mid value, I mean 10 divided by 2, 10 plus 10 divided by 2, that is actually 10. So low value is 10, high value is 10, mid also be equal to 10. So A of mid equal to element, that is 112 equal to 112. Yes, it is true. So therefore here your search is success. Okay. In this way, so the operation will be recursive calls will be gets happen towards right side, towards left side, towards right side on elimination of the list. On elimination of the list, it is going to happen. So towards left, towards right, towards left, towards right continuously. Okay. In such a way, so this is the first and foremost. This is the first and foremost searching in the whole list. At right hand side, this is the second search operation. At left hand side, this is the second search operation. And then come to right hand side, this is the third between so 7 and 11, this is third search operation. Between the what you call 11 and 14, this is third. And here also same. Here also you have to assume in the same similar fashion. For taking this one, what is the decision making tree for binary search? Initially, it is going to search with element, index value 7. Afterwards, it will be goes to 3. So look at this. 3 will be taking as a consult bit will be 3. This is the second search operation if your element is available at the left side. Still left side, it will be goes to 1. Okay. Still, if the element is not available, obviously you can say not found. So if element will be right side of 1, then it will be goes to 2. Okay. So look at this. This is the first position. This is the second position. This is the third position, and this is the fourth position. I hope that you understand. First is not position. First mid, second mid, third mid, and fourth mid. Okay, you can see. In that way, it is going to search the element. If still element is not taking this one, then it will be go ahead with F5. So first is gets over, second is gets over, and this is third one. Look at this, F5 will be third one. And here also two more possibilities are there. Either it is available at F4 or F6. So left side, this is 4. If element is not available in this way, then it could be taken right way. It is also 4th position. Okay, left hand side searches are being gets over. Then come to right hand side. So first one is at 7, and if our element is greater than F7, then we'll go to second search operation will be takes place at F11. So then it will be taken left hand side in the sense 9 will be taken at third search. You can observe this one, third search only. And then here 8 will be taken fourth search. Still it is taken towards left side. This is 4. Time being, so F11 is not equal to element, and F11 element is less than the mid, then it will be goes to, I'm sorry, F3, F9, 101. So this particular element is not really equal to, so our 112. So this will be taken greater value. So greater value in the sense it will be goes to, so here it is 4th search. The problem will be taken something like this. Similarly, here also same. This is the decision-making tree. This is the decision-making tree for binary search. For example, n value equal to 40. N value equal to. So while plotting the elements, you must follow the rules and regulations of the binary search. What are the rules and regulations? So AF1 is less than or equal to AF2 is less than or equal to, and so on, AFN. Okay, AF1 is less than or equal to AF2, less than or equal to AF3, less than. So that is all elements which are available within the binary search must be in non-descending order. That must be there with you in our mind while the binary search gets operated. Okay, this is the binary search decision-making tree for number of elements equal to 14. So this decision-making tree cannot be the same for number of elements will be equal to 20. If number of elements will be increased, this decision-making tree cannot be the same. Okay, if number of elements will be decreased, for example, only 10 has been taken, decision-making tree cannot be the same. For exactly equal to 14, so this is the way you can identify it. Okay. That. Actually, I'm trying to explain this one also, but the time could not be supported. Only 8 minutes are there with me. Let us try. How the complexity will be evaluated. So how this could be evaluated here in the sense, let us consider, so you have only one input. The list might be having just one input, that is some 20 for example. And the element to be searched also equal to 20. Or if this is the case 1, in case 2, element will be equal to, so searched element will be, X will be equal to some 70. This is case 2. In case 1, yes, only one element is there, is successful. In case 2, it is not successful. Okay, single element is there. 20 equal to 20 in case 1, yes, it is true. So therefore, element will be get succeeded. Yes, your search is succeeded. In case 2, our input 2, so 70 is the element, so it could not be 20 equal to 70, it is not true. Your blind search is unsuccessful. However, whether it is success or unsuccess, it doesn't matter for us. So finally, one element is there with you, then obviously we can take so 1 unit of time to complete this particular operation. Only one comparison is required. Okay. Therefore, that one comparison will be total number of elements will be n. So where n will be equal to 1. So therefore, so total, number of units of time which will be taken for solve this particular problem, where n will be exactly equal to 1. Okay. So simply speaking here, instead of n, you could also write something like this. So t of so 1 will be equal to 1. T of 1 will be equal to 1. You could also write something like this. Then, if consider more than one element, more than one element in the sense probably 2 elements, probably 20 elements, probably 1 lakh elements, or probably 1 crore number of elements, however, whatever it may be, but it is not equal to 1. Then, so the time complexity will be calculated something like this. T of n equal to, so here we would like to consider, what exactly we are trying to consider here. So one sublist is not being taken into consideration. One sublist is not being taken into consideration. So 2 is not available here. 2 into T of n by 2 plus f of n equal to C. Number of comparisons will be done. Constant number of comparisons will be done in the binary set. Every time we have been taken, so 3 comparisons. A of mid will be equal to element or not. So whatever A of mid will be equal to element or not. So element is greater than A of mid, or element is less than A of mid. We'll consider whether they may be completely executed the 3 instructions or not. That doesn't matter. But for every recursive call, these 3 comparisons will be gets happen. So that is why we like to take C, a constant. And if you consider the binary set, if it is, A of mid not, in the first recursive call, A of mid is not equal to the required element, and we're looking forward for whether it is the left side or right side. If it is left side, right sublist is eliminated from the set space. It could not be considered endeavor forever. If it is not in left side, if it is in right side, left sublist will be completely eliminated, and you never across that particular list. So that is why here A will be equal to 1, B will be equal to 2, because it is divide and conquer. Equation 2, and consider already we have T of n by 2. So T of n by 2 value will be T of n by 4 plus same number of comparisons, equation number 3. Again, we have to find the value of so T of n by 4. T of n by 4 will be, again, so the sublist will be divided into 8 partitions. So that is T of n by 8 plus C, same number of comparisons in this recursive call also. So it is equation 4. What we are supposed to do, equation 3 and 4 will be submitted or substituted in equation number 2. If you substitute something like this, it will becomes in such a way. T of actual equation number 2 will be T of n equal to T of n by 2 plus C. Within that you have to submit it something like this. T of n by 2 value is from equation number 3, T of n by 4 plus C, and this plus C will be taken here. Then T of n by 4 plus 2C. And we have T of n by 4 value in equation number 4. Substitute that value here. That is T of n by 8 plus C. Okay. And already this 2C will be taken here. Okay. This will be T of n by 8 plus 3C. C plus 2 plus 2C equal to 3C. Then it will be, let me consider, so convert everything, where exactly it could be possible, convert everything in 2 powers. T of 8 will be converted into 2 powers, so therefore T of n by 2 power 3 will be plus 3C will be the next one. If this process will continue for k times, we don't know. Only 3 elements are there, only 8 elements are there, only 20 elements are, we don't know exactly. So that is why Based on the number of elements, we'll continue for k number of recursive calls. Therefore, T of n is equal to T of n by 2 power k plus kc. You can see, so ranges 2 ranges 3 also equal to the same constant here, that is 3. Okay. This is equation number 5. Now let us consider the primitive, basic primitive of divide and conquer technique, that is n equal to 2 power k. This is the basic primitive. When n equal to 2 power k, so whatever the problem specification, so it could be divided into single list of elements or 2 by 2 matrix as far as so the Stresson's matrix multiplication problem, something else, it could be taken. So let us take this as a small one. And then apply log base 2 on both sides for equation number 1. Log base 2 log base to n equal to log base to 2 power k. Then log base to n equal to k into log base to 2. Log base to 2 equal to 1. So therefore k equal to log base to n. So this is equation number 2. Substitute these two in equation number 5. Okay. And you could get this one. This is actually equation number 5 it is. So this equation number 5 will be taken something like this. Then T of n by n plus log base to n. Instead of n, instead of 2 power k, I'd like to substitute n, and instead of k, it could be substituted as so 2 power log base to n. And T of 1 into plus c into this one here. Then 1 plus c log base to n. So 1 is very negligible value when compared to this one. And so c is constant, we'll eliminate that. This is the way. Okay. This is the way you can see. So let me explain this one. By tomorrow, there is no problem for